We're recording now. It's July 5th, 2017. This needs to move. There we go. Okay. All over B minus A. Right. So for a graph, if I put in x squared minus 3, x squared minus 3, and we put y equals, right? Here's the function right now, right? And if I want to know the average rate of change from 0 to 2, right? From 0 to 2, then what am I really asking about? The slope, that's right. And so when I say f of x equals x squared minus 3, right, on the interval 0 to 2, and I'm asking about f of b minus f of a over b minus a, then I'm asking about the slope of the line from this point to this point, right? Questions on that? So that it gives me an idea of the change from this point to this point, but oh my goodness, I don't want to know the change from this point to this point. I don't want to know the change from this point to this point. I want to know the change at this point exactly. This point exactly, right? And so in some sense, I want to know how fast you're changing at this point. That is the calculus question. How fast am I changing at this point? Now, those two questions are related, right? That if I know, and oh my goodness, geniuses over centuries have used this method, that when we want to know something that's at a particular point, we use what we know at some other points around it, right? That if I know the slope from here to here, right, it might help me find the slope from here to here. And they're roughly the same, right? That the slope from here to here might be whatever we mean by the slope at this particular point, right? How fast am I moving up here? Okay. And so what we're going to do is we're going to approximate the slope here by taking slopes surrounding this point. Okay. That's what we're going to do. And I'll explain that differently in just a second. The derivative is going to be the slope at this point. So the derivative at 1 is whatever the slope is here. Is the derivative positive or negative at this point? How do you know? Because I've heard a lot of different things, because it looks like that the function is going up here. It looks like if there's any reasonable justice-induced definition of derivative that, and if the derivative represents the slope, it clearly looks like the slope would be positive here, right? Okay, so the derivative is positive. Anyone know what the derivative at 1 is here? It is 2, right? 2 units per unit, right? So the derivative, so the slope here is 2. Now, if it is the case, let's suppose that that's right, that now, give me the equation of the line that's tangent to that point. So I'm gonna trust you. There it is. Let's assume the slope is 2, right? So that means that somehow I should use a different color. That means that somehow When I look at this there, the slope is 2. Okay. Well, I asked for a line, right? What do you need for a line? What do you need for a line? A slope and a point. Okay. My favorite. Usually we are in one camp or the other. Y equals mx plus b. You people. Point slope. My favorite. Right. We give you a point and a slope. Okay, that's one. Now, I have the slope. Seems like it's 2. We'll see if that's right or not. Or at least we'll get an idea whether that's right or not. I need a point. What's the point?
1 negative 2.
1 negative 2. And if I didn't give you the picture, how would you know? I gave you the equation y equals x squared minus 3. I told you that x was 1. And so you can plug in 1 here and get negative 2. Y minus negative 2 equals 2 times x minus 1. Y plus 2 equals 2x minus 2. Y equals 2x what? Minus 4, for sure. So what? What does that mean? That means that if I go here now and add y equals 2x minus 4, right, then around this place, they look identical. Right? This means tons of things. Right? This means that if somehow x squared minus 4, if my daughter comes to me, she's 6, and I say, yo, tell me what x squared minus 4 is when x is 0.999, right? She doesn't really know how to square something, right? But she wouldn't be that far off if she took the 0.999 and plugged it into 2x minus 4. Right? Because 0.99 is really close to 1. And if you're close to 1, then x squared minus 3 and the lines look nearly the same. Right? So that's called linearization. We'll talk about that at the end of chapter 2. That when functions have derivatives, right, what does it mean? What does it mean to have a derivative? What does it mean to have it? We just showed it. What happens when you zoom in on that function? What does it look like? Say it again? That's right. But forget about the line. If I took the line away, it looks like a straight line. Who said that? Thank you. It looks like a straight line. Right? That's what it means to have a derivative. Okay? That's what it means to have a derivative. That's what it means to have a derivative. Anybody want to write that shit down? That's what it means to have a derivative. I'm going to ask you that. Right? By the way, I want to be clear. I'm going to roll through, and if you roll out of this class and you don't know what the derivative means, it's an automatic F. Hands down for just one moment. If you roll out of this class, you don't know what the integral means, you don't know what the derivative means, I just cannot pass you. Drones do not leave this one. Not this class, right? You got to know what stuff means. I had hands. Please, go ahead. Absolutely. Thank you. Whew! I love it. I love it. That's like my crack. Explain that again. That's good. That's good. So let me see if I can do this here. I want to zoom in. Oh, can I do this? Oh, Lord have mercy. Right? When you zoom in, I can't tell the difference. To have a derivative means that locally you look like a line, look like a straight line. Right? That's what it means to have a derivative. Okay? That means when you zoom in on it, it looks like a line. Is that okay to answer your question? Yeah. There's another question.
Oh, it was more like I was gonna say like you
Clarify. Absolutely. Thank you. Yeah. Excellent. 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 Good. 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 So now we're in mathematics. I got to give formal definitions. I got to talk about, so today it's just a feel. I'm giving you why we're here. I'm giving you the general feel. And again, my people who've had calculus before, you know where we're going. I hope I'm filling in some holes. Again, you know how to do all of these rote things, right? But concepts, that's what we're talking about today, right? Now, in order to get that line, right? By the way, there's a big hole. How'd you get the number 2? Right? We got to answer that. How'd you get 2? Right? Some people know it from the definition. Right now, we got 2 magically. Right? So we got to fill in how we got. We have to return back to this exact function later and show that the derivative is 2, that slope is 2. Okay. Now, in order to answer this question, there are some technical things that we need to answer, right? So that when we go back here and I ask, well, how fast was I going I started at noon at 12:31 p.m. How fast was I going then at that moment? Right? Of course, my physicists care about the other question, right? That, of course, you throw a ball in the air, it falls, hits the ground. How fast was it moving when it hits the ground? How fast was it moving when it hits the ground? How fast was it moving when you threw it? So, as you may know, we are on this big blue planet in this universe. Everything's moving, right? And I want to know, how fast is that asteroid moving right now? Not between 12 and 1. How fast is it moving right now, right? So that physics is very much tied into calculus. Of course, physics and mathematics, we have this pull and tug over this dude Newton and who he belongs to, right? We're in the math class. I know you're going to see physics people later, but he's ours. The inventor, discoverer of calculus, along with Leibniz, answered questions like this, or at least formulated it in a way that we could answer these types of questions, right? In order to answer this question, of course, we don't know that much, but we're really good at using what we know to figure out what we don't know. Well, I was able to find the average speed from here to here. As a matter of fact, if I had all the information about my speeds on this entire interval, right, or my location on this entire interval, then I'm able to pretty much approximate what the speed is at this point, right? Because what I'm able to do is that if I know, meaning if I have a function that depends on time, if I know my distance at any time, then I should be able to approximate this number, right? The speed, right? And here's how, right? I would do that because I would be able to approximate it because I know the average speed. So I found the average speed from here to here, but I can find the average speed from here to here, right? And if I find the average speed from here to here, it might be close to what the speed is at this moment, right? But if I want to get closer, then I can find the average speed from here to here. And if I went along and I said, well, I know my distance here, and I know my distance here, and I knew how long it took, then my average speed over this time interval might be close to what my speed is at that moment. But why would I ever stop? Right? I can find the average speed from here to here, and then from here to here, right? And just keep zeroing in on the moment that I care about, right? That's why we're talking about limits first, right? Because it's that limit process about narrowing down on the specific place in question, right, that we are interested in. And this is why we have to start at limits. I care about what happens when I take the time closer and closer to the time I'm interested in, 12:31 p.m. Okay. Now I have to spend some time formulating all of that, right? So we're going to have a function, and now we're going to talk about limits, right? There are a lot of things going on here, right? There's some assumptions, right? When I'm driving, I didn't give this response to the cop because he might have arrested me. But at the end, he says, you were driving 100 miles per hour on average. I mean, on average, but I know there was a moment in which you did. I say, well, no, not really. You know, did I tell you about this trip? I went along here, and then all of a sudden, I just plopped right here. Right? I just went from here to here, right? I just went from here to here. And he would arrest me because he thought I was on drugs, probably, right? Why can't I do that? Right? It's just not possible. The realm I'm in is precisely the word he used. It's continuous, whatever that means, right? So that if I'm asking about a derivative, I need to be in a continuous world. Right? In order to have a derivative, you better be continuous. In order to have a derivative, classic true-false question. In order to have a derivative, you need to be continuous. And it's from this problem, right? So he assumed correctly that I can't just jump around. I can't be here and here and I just can't do that, right? That if locally I look like a
Straight line.
if I locally I look like a straight line, then you can't tell me I can jump around. Right? So what does that look like when we graph this function? Right? When we graph this function, if I could skip around, we're talking about graphing something that looks like this. Right? Bam, bam. No! Whatever's going on here, I would never, ever ask about a derivative here. Never, 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 never. And while we're here, would I ask about a derivative here?
No.
Why not?
There's no change. There's never any change.
So this is good. So I got some people who are telling me stuff that they may have learned before, but I want to be clear about something. In this class, I'm starting from 0. I'm assuming you know nothing. So if I'm asking you this, you can answer it because of something I already said, something we already agreed upon. When I zoom in on this, does it look like a line?
Yeah.
When I zoom in all the way on this thing, let's do it. Absolute value, right? Looks like an absolute value function. Oh, I don't even know how to put in the absolute value in this thing. Let's see. Oh, I can just turn that off. That's so sweet. Okay, y equals, I think it's ABS. If there's any justice in this world. Oh, it's not the absolute value. Oh, how does it not know what the absolute value is? You think it's going to work if I put 2 bars? Say it again. Oh, there it is. All right, so here we go. We're claiming there's a problem at 0. Zoom in on it, 0. Does it look like a line? No. Derivative? No. Questions? Right? About that? So we said, so this is all just on intuition. I don't care about, well, rate of change. We haven't defined any of that. We said intuitively what it means to us is that locally, when you zoom in on it, it should look like a straight line. When at 0, no matter how close you get to 0, it looks like a... What does it look like when you zoom in on 0? Always.
Point.
It looks like a V, right? It looks like a V. No matter how... Zoom in as much as you want. From one side is going down, from the other side is going up. That's not what a line is, right? Intuitively, okay? So yeah, we're trying to undo all of this memorizing stuff. Make it make sense to you. Okay, great. All right, so we need to be talking about limits. So from this, again, we need to be talking about getting closer. If we're interested in this point, we need to be talking about getting closer and closer to this point with something that we know. Okay, so I want to talk about what that means. We are going to need a function of x be a function. So we want it to be well defined. What does that mean? That means for each x, there's only one y value, right? Excellent. We say that the limit as x goes to a of f of x is equal to L if what? That's correct. I haven't defined any of those things, so I can't say that as the definition. We're going to demonstrate that. That's correct. What's the definition? How do I know? So here's the deal. 8 o'clock. Were you here at 8 o'clock? In this room? Yes. Right? So we would say that your limit as the time went to 8 was this room, right? How would you convince somebody of that? As the time got closer and closer to 8, where were you? To the room, right? That's what everybody says. That's not what Weierstrass meant when he created the definition for this, right? So I'll say it this way. I'm going to say it in a couple ways, right? So I'm going to say it the way that we're used to hearing it. If f of x, don't write this one, gets closer to L as x gets closer to what? Gets closer to A. Now, this is a definition in quotes. Okay. Meaningless. This is meaningless. Why? Because what's the word that's so ambiguous, has no real meaning? Close. Means nothing, right? Because close for you is not the same as close for me, right? But what this does, though, is it gives us some intuition about what we mean, right? So that when we say something like the limit as x goes to 5 of x squared plus 3, we would like to say that that is what? What is it? 28. Okay. So, how do we get that? Plug in the 5. Okay. No. It's not just because we're plugging in the 5. Okay, so this is good. So when I write this, right? When I write this, I'm appealing to the definition. Now, we will get to a point in which we will be able to say that we can plug in the 5, but not at this point. Why is this 28? Because we're making the claim that this gets closer and closer to what? 28 as x gets closer and closer to 5. That's the reason. It has nothing to do with plugging in the 5. So this statement is true and has nothing to do with plugging in the 5. It has to do with this getting closer and closer to this as x gets closer and closer to 5. Okay. Is that okay? And so, of course, the mathematician would say, here's f of x, right? And so f of x is x plus 2 if x is bigger than, let's do this, if x is not if x is not 5 and it's 38 if x is 5. Okay? That's what I want f to be. I just defined that. That's my function. I called it f. Let's look at some values. What's f of 3? F of 3 is 5. How do you know? Because I've given you a rule that if you give me a number that's not 5, I want you to add 2 to it. Okay? F of 7?
9.
9? Questions? 7 is not 5. So I'm going to take the 7 and add 2 to it. What's f of 5?
38.
Questions on that? My crazy function, if you give me 5, I'm going to give you back 38. You know what I'm about to do? What's the limit as x tends to 5 of f of x?
Oh, wait, no.
It didn't exist, no.
I'm hearing all sorts of things. This is excellent. Right? So I'm hearing 7. I'm hearing 38. I'm hearing there is no limit. One of those is right. Okay. So I brought this up because of your comment, right? F of 5 is 38, right? What should we go back to? What should we go back to? No. No. What the definition? The definition. The question is, what does this get closer and closer to as x gets closer and closer to 5? So if I wrote this, what's the limit as x goes to 5 of x plus 2? What's that?
7.
Oh, yes, that's right. Not because we're plugging in the 5, but because when x gets closer and closer to 5, but not equal to 5. But not equal to 5, right? I don't care about what happens at 5. X is it's getting close to 5. That's 7, and oh my goodness, this is a test question for sure, right? This distinction, right? And the reason why that matters is that we're not going to care what happens at the number because bad things happen at the number, right? And we already know that bad things happen at the number, right? Because if I want to know how fast I'm going at a moment, right, I'm doing the average rate of change around that moment, right? So if I'm doing the average, that's one number divided by another one, right? So I'm doing one number minus another divided by something else. Let's go back. Look at this. Look at this right here. Look at that average. Tell me about this denominator, right? So is this number really close to this number? Yes? They're really close, right? So what is this denominator going to when I subtract? It's going to 0. The denominator is going to 0. I'm going to eventually be dividing by 0, right? But somehow things still work out, right? So that when I calculate this derivative, when I calculate the actual speed, the denominator is going to be 0. But thankfully, to help out, what's the numerator going to be? That's also going to be 0. And then they'll fight and we'll get a nice number, right? But the point is that if you plug in something and get 0 over 0, we have no idea what that is, right? So every time you want to calculate some derivative, you'll find out that we always get 0 over 0 if you plug in the number. So we don't ever want to plug in the number. We care about what you're getting close to, right? So don't worry about plugging in the number unless we have a theorem that says that you can, right? So there are going to be some instances where you can plug in the number and it works out, but in general for limits, don't worry about plugging in the number. Worry about what the whole thing's going to as you get closer and closer to the number in question. Right? That's a big distinction. I had mentioned to not write this down because this is not really what mathematicians had in mind. So here's why this is bad, right? So if I give you if I give you 1 over, I'm going to give you 1 over x plus 1, right? 1 over x plus 1 looks like this. And it goes down. What does it go down to? 1, right? So there's a what at 1? What do we call this line? A horizontal asymptote at 1. Is that okay? So this looks like it goes to 1. This is y equals 1. But what I want to say is that the limit as x tends to, now where is x going in this case? I haven't talked about this, but where is x going now?
Positive.
Right, so as x goes all the way to the right, it looks like it's 1, right? But if we use that definition that we have written, why wouldn't it be 0? Certainly, as x gets bigger and bigger, this does get closer and closer to 0 too, right? Right, it's going down, and so it's closer to 0 than what it was. Why is this not 0? Why is this not 1/2? It's getting closer and closer to 1/2, but just not close enough, right?
Yeah.
Just not close, whatever that means, and that's the problem with close, right? That I could say, well, it is getting closer and closer to 0. He's like, well, no way, it's not getting closer and closer to 0. So what is it that we mean when we say that the limit is 1 in this case? So let's try and make sense of it. So the limit as x goes to 2 of 4x plus 1 is equal to, what is it?
9.
It is 9. Right? And so this argument is due to Weierstrass. He says that, look, this is 9, right? And then you say why, right? And so what he does is he creates this skeptic, this person who comes in and she says, no, I don't believe you. You have to prove that to me. And then he proceeds to prove her wrong, right? Here's how. So he says, I believe that the limit is 9. And then she says, well, I don't believe you. And then she says, okay, well, if you don't believe that that gets closer and closer to 9, then you must believe that if it doesn't get close to 9, then it has to do what? If it's not close to 9, then if it's not close, then it has to be far. Right? I don't ask difficult questions. If it's not close, then it's far. Right? And then she says, yes, that's right. Not close means far. And then he says, well, tell me how far away you think it is. And then she provides a number, and then he gets closer. It's that simple. So every time she says, I think you stay away by this much, then he just finds a value of x close enough to 2 that's closer than what she said. And then she says, well, no, wait. I'm sorry, I changed my mind. And then he says, bring it on. And every time she says, no, I think you stay this far away, then he finds an x that's close enough to 2 that gets closer than what she said. Right? So that if we had a full barometer of where you were all day, then you could easily shut down anybody when Ty comes in and says, you weren't here at 8. You were not here in this classroom at 8. And then he says, oh, no, I tracked my whole time. I know exactly where I was. And then she says, no, you were late. You weren't on time. And then you say, well, if you think I wasn't there, then you think I was away from this room at 8. And she says, that's right. And then you say to her, well, where was I? And then she says, well, you were 5 feet away the whole time from the room. And you say, oh, no, at 7:59, I was 3 feet within 3 feet of the room. And she says, oh, that's fine. 3 feet it is. You were 1 foot away from the room the whole time. And she says, oh, no. At 7:59.8, I was within 2 centimeters of the room. And then you just keep going through this, and every time she says that you weren't here by some distance away from the room, you're able to say, oh, but I was. And she says, oh, I guess you were here. Right? So, the definition is not that this gets closer and closer to this as this gets closer and closer to this. It is this. It is that I can make this as close to this as I want by making this sufficiently close to this. I'm convinced that this limit is this if I can make this as close to 9 as I want by taking x sufficiently close to 2. So that when the skeptic says, can you make this within 0.000001 of 9, you say yes by picking x to be within 0.000001 2. And if you can do that, if you can make the difference between these two as close to 0 as you want by picking an x close enough to 2, then that means this is true. Right? I'll write that down in just a moment. That moment would be now. Can make 4x plus 1 as close to 9 as we desire simply by picking an appropriate x close enough to 2. And so this eliminates what's close for you and what's close for me. If anybody comes to you and says, here's what close is to me, then I can find an x that will be closer. No matter who comes, right? And again, this is due to Weierstrass. So again, this is not formal. He talks about epsilons and deltas. For every epsilon greater than 0, I can find a delta such that for every x within delta of 2, f of x is within epsilon of L. Right? That's his ridiculous, like, mathematical definition that my mathematicians will need to know in the future. Right? So that's about 3 years from now, my math majors will need to know that definition exactly. Right? So for every epsilon greater than 0, there's a delta such that. So all that means is that the skeptic comes in and says, I think you stay that far away, and you say, oh no, I can get closer than what you think by picking x close enough to 2. So the epsilon is the distance away from 9. The delta is the distance to 2 for x. Okay. So this is good. So you've got an idea of my style, right? So what will happen is, what I want to do is, so I have 2 identities. I have 3 identities. So there's me, the mathematician, there's me, the teacher, and then there's me, the grader. Okay, and the grader only comes out 3 times a year. Okay, but the mathematician in me just spoke. Okay, along with the teacher. The teacher in me also wants to make sure that you understand, and also wants to get to the point of what you're going to need to do for the homework and all that other stuff, right? So I'll navigate in through those 2 personalities, right? So I'll talk conceptually about stuff, and then I'll talk pragmatically about stuff, right? So there's a pragmatic side, there's a mathematician side. So I'll jump between both of those. I will take any questions about this formulation. In general, you can replace 4x plus 1 with f of x, 9 with L, and 2 with A. We'll do that. In general, when we say that the limit as x, this is question number probably 2 or 3 on the test. Define, write in words what this means. here it is. F can be made sufficiently close to L by taking X, I should say f of X, by taking X sufficiently close to A. Right, so I could ask this question in all sorts of ways. Right, I could say, what's wrong with the following statement? That the limit as x goes to a of f of x is L if f of x is closer and closer to L as x is closer and closer to A. What's wrong with that, right? And you would just say, what this really means is that. Or I could say, what does that mean in words, right? That means I can make f as close to L as I want by taking x as close to A as I need. In the last 5 minutes, I want to give you a idea of what some of the homework looks like. You'll have to go in and play around of how to enter stuff in the homework, right? This is why I made the homework due on Sunday at midnight, so that you can play around with the interface. It'll be pretty easy to answer in stuff. And when you go in, there'll be videos about how to do problems and stuff like that. This video will also be up as well that we are recording. And so I'm not expecting the homework to be done tonight. That's why I made the due date Sunday at midnight. Here's a graph. Let me make it smaller. This is a picture of the problem that I wrote analytically earlier. All right, so here's the function f. Is this a function? Passes the vertical line test for sure. Every black dot represents a value for some x. This is defined on the whole real line. So 2, for instance, goes to 4. -3 goes to 0. Questions about that? -1 goes to -3. So you just need to put -3 here. F of -1 is -3. Now there's some things I have not defined. Okay. So when we talk about the limit as x goes to A from the left of f of x, and the limit as x goes to A from the right of f of x. Now we're here where you were alluding to. Your name? Max. Now we're here, Max. The limit from the left and the limit from the right. And what we want to do is take advantage of 2 dimensions. That the domain, the x values, are lie on the line. Right? And so let's talk about what this means. When I say that's M and when I say that's L, this means that I can make F sufficiently close to M by taking values of X that are close to A, but, which means what? Smaller, right? But smaller, right? So F can be made close to M by making X close enough to A, but from the left, which means on the number line, you're smaller than A. We'll talk about what this means pictorially in just a second. You might imagine what this one says. Here, F can be made as close as I want to L by making X close to A but larger. There's a theorem that says, let's write the theorem. The limit as x goes to a, if, a theorem is just an if-then statement. Here's the if. If the limit as x goes to a from the right of f of x is equal to L, and the limit as x goes to a from the left of f of x is also equal to L, then the limit as x goes to a of f of x is what? It better be L. If the limit from the left is 5 and the limit from the right is 5, then the limit better be 5. Right? What happens the other way? What if the limit's 5? I'm going to tell you that the limit's 5. What's the limit from the left? What's the limit from the right? Sounds like an if and only if thing, right? That if the limit from the left and from the right is 5, then the limit's 5. And if the limit is 5, then the limit from the left and the limit from the right also have to be 5. We'll talk that through tomorrow. But as we answer this question, when I'm talking about the limit as x goes to -1 from the left, then that means I'm riding along this thing. I should use a different color, but I'm riding along this graph until I get to -1 on the left. What's the limit on the left? 2. Wait, there's nothing at 2. So what? That's right. There's nothing at 2. So what? So the answer 2. The limit from the right? Right. It's 1. The limit? There is no limit. Okay. So I never said this. We want the limit to be one thing. Right? We want the limit to be one thing. The limit should be unique, and we understand that, right? When we're driving and someone puts the radar in me, I can't be driving 72 miles an hour and 45 miles an hour, right? The limit has to be one thing, right? The derivative better be one thing, right? So that if from the left it's 2, from the right it's 1, there is no limit. You literally type in the letters D and E into the system. And you'll see it, right? You'll see a little button that gives you, it says put in a number or a decimal, or if there is no limit, type in D and E. Okay? We'll end there. Tomorrow we'll truck along, less introductions. We'll come right in, right at this spot, and we'll hit the road running. I will let you know that we have a week. If you have just been blown away what I talked about today, there are 2 things. Number 1, today was pretty heady. Okay, I will get more concrete. And number 2, there's a week, right? I think you have to switch to another class, right? So if you want to go to the other calculus class that's going at a slower pace, feel free to do that, right? But I do want to support you in this space. So if you feel like you can hang on, give it a couple more days, you can also do that. There's a question on the floor. It's Sunday at midnight, and then there's there's another one after this that's also due Sunday at midnight about the derivative.
Can you access those already?
Yeah, I think they're already open.
There's just 2.1 that you assigned today.
Right. I'm sorry, they're assigned today. They're due Sunday at midnight.
I don't know what I'm saying. It's 2.1.
It's 2.1, and I believe it's 2.2. Yeah. And I'll be there tonight at the study session. If you want to talk, anything else, we'll look at the space about what that looks like. Yes. Oh, you're very welcome. Thank you.
Thank you.
Oh, you're very welcome. Good questions today. I'll turn off the recording, and again, I'll put it up.